The F-18 fighter jet has some of the biggest leading-edge extensions going around. Leading-edge extensions, LEXs, are, as the name suggests, these extensions from around the near of the cockpit, running all the way along the fuselage, usually towards the wings, and they blend towards the wings. For the F-18, they extend literally from the very start of the cockpit and even a little bit further upstream from that, all the way down to the wings. It covers like a quarter or even a third of the entire airplane. They're huge. And while some other airplanes have featured them, for example, the F-14, often, they are part of another system. Like for the F-14, when they blend into the delta wing of the F-14 when they sweep the wings back to go supersonic. So the F-18 was also one of the first fighter jets to ever feature these LEXs, and as such a big geometry. So how do they work? Well, about a month ago, we did a podcast on the LEX Aerodynamics, and this was at the request of one of your amigos, Hari03. But while that podcast 163, went through the aerodynamics in general of these LEXs, it didn't cover the dynamic performance of these things. So as we know, fighter jets and all airplanes really don't exist in a static mode. They move around, they turn, they ascend, they descend, they pitch, they roll, you name it, that's what they have to do. As such, the jet is dynamic. They don't exist in like this little frozen time capsule where they're just going at one angle of attack. Sometimes they do, sometimes they are just cruising along, but a lot of the time they are changing direction. And that's really what they are built for when you think about it. And if you want to learn more about how these LEX aerodynamics in steady state conditions operate, then check out our podcast 163. But just in a nutshell, these LEXs produces vortices that travel along the top surface of the LEXs, and then these vortices help keep the flow attached at high angles of attack, much like on a delta wing. That allows the F-18 jet to fly at much higher angles of attack and still produce lift. Now, at a certain angle, these vortices will pop, and that results in a sudden change in force acting on the jet, because all of a sudden you have this loss in lift. Now, that not only means that the plane can't fly as it was just flying before the popping, but also the pilot now has to wrestle the plane back to a flight condition that is stable, that is dangerous. Now, things get even more interesting when we consider how these vortices forming on the LEXs behave when the plane is pitching and yawing. So let's say you want to fly at an angle of attack of 40 degrees. To get there, obviously you need to go from 0 degrees to 40 degrees, or some other position to 40 degrees. That is a dynamic motion. Does that movement affect the vortices? Does it affect the vortex breakdown? That is what we're looking at today in this podcast. We're looking at the hysteresis of these vortices with pitch and yaw angles. Now, that is a funny word, hysteresis, and personally, I didn't even know that it existed until I was like 21, and I don't think I was a bad English student, but I just didn't come across it. So the word hysteresis, what does that mean? Well, it refers to whether something's performance is in the exact same conditions changes depending on how you get to those conditions. So as an example, we can have the jet pitching up to 40 degrees, or we can have it pitching down to 40 degrees. Those are two different paths that it can take to get to 40 degrees. But does that affect the performance of the jet and of these LEXs? And often an object won't have any hysteresis, which means that approaching the same condition from different initial conditions won't affect the object's performance at the end condition reached. But sometimes an object will have hysteresis, which means that depending on which way you come to that condition, that will affect how the object will perform at that end condition. So one common example is an airfoil. When you pitch an airfoil at a too high angle of attack, it stalls. But then if you try to get the flow reattached over the airfoil, usually you can't just pitch down to the same angle that the stall just occurred at or just below the stall. You won't get the flow reattaching there. You actually need to pitch it down quite a lot to regain the flow attachment and continue to produce lift. In this case, the airfoil is suffering some level of hysteresis. So to look at how an F-18 jet's LEXs perform at different angles of attack and different pitch and yaw rates, we are going to look at a master's thesis from the US Naval Postgraduate School. If I scroll up here. It is called a flow visualization study of LEX generated vortices on a scale model of an F-18 fighter aircraft at high angles of attack. And this is free to the public, so you can find it in the link below. So to look at the LEX aerodynamics at different pitch and yaw rates, this researchers went into a water channel. So that's pretty cool. We don't cover a water channel every day on this podcast, but they are pretty cool and they are very useful at a lot of times. So let's cover what their setup was and this water channel, because there are a few points that are interesting. So the water channel itself had a test section of 15 inches wide, so about 38 centimeters wide, 20 centimeters high, so about 60 centimeters high, and 60 inches long, so about 1.5 meters long. Something cool with this water channel is that the sides of the walls on the sides slightly diverge to compensate for the growing boundary layer. So as you go downstream, the test section actually gets wider. So why is that important? Well, as the water, as any fluid really, travels over a surface, the boundary layer grows. We know that. But in terms of a water channel or a wind tunnel, that boundary layer growth results in a smaller test section, effectively because now you have the slower moving fluid taking up space. That fluid there, that boundary layer, doesn't have a lot of momentum. It doesn't have a lot of displacement thickness. And if you don't know what this means, if you don't know what the momentum thickness or the displacement thickness of a boundary layer is, check out two of our actual YouTube videos called Aero Fundamentals number 36, Boundary Layer Displacement Thickness, and Aero Fundamentals number 37, Boundary Layer Momentum Thickness Explained. Both of those videos will take you through what these mean and how they affect the flow around a boundary layer. And so for this test section, with increasing boundary layer thickness, in order for the free-stream flow to continue down the channel, it needs to speed up because there is less cross-sectional area for it to flow through because the boundary layer is taking up some of that area with this slow-moving fluid. And from the mass flow rate equation, if the density of the fluid remains the same, then for a shrinking cross-sectional area, for the exact same mass flow rate to go through, the velocity needs to increase. And because we don't have a compressible fluid here, it's water, it definitely has to increase to get through that smaller cross-sectional area. As such, the velocity has to increase, and from Bernoulli's equation, we know that if the velocity increases, the pressure must drop in this free stream flow. So that means that as you go downstream, if you don't have these walls diverging a little bit, the pressure will actually drop a little bit. So when you play around with velocities and pressures, the flow physics will be affected too around the object that you are testing. That's just a fact. So to get around that, diverging the walls as you go downstream is a very common and generally pretty good way of solving this problem. Now, the amount the walls need to diverge changes with the velocity of the fluid, but unfortunately, it is very difficult to have walls that can change, especially in a water channel. So you usually just pick a velocity that minimizes the effects of the boundary layer across the entire range that you're looking at, or just pick one velocity that you'll be using most that you're really interested in and design the tunnel for that. Either way, having this diverging channel is good. Now for this water channel, it had a turbulence density level of 1%. This is pretty high. The velocity uniformity, which means how much the velocity changes as you traverse the test section or cross section, changes 2%. Again, this is a little high, but something that isn't often talked about is that it is usually harder to get a good quality flow in a water channel than a wind tunnel, because for one reason, the pump pumping the water around creates vibrations, and those vibrations are transmitted through the water quite easily through to the rest of the test section. So we do get some vibrations in there, increased turbulence density, etc. As such, the pump often creates a worse quality flow. So it isn't uncommon to see such high numbers for the turbulence density level and velocity non-uniformity in a water channel. Now, this water channel had 6 pressurized canisters with food coloring in them, and this food coloring was injected into the flow to visualize what's happening. That's a pretty cool contraption. So the pitch and yaw were controlled via 2 motors, and the next part is really funny because it shows just how far we've come technologically. So these pitch and yaw angles were controlled with these 2 motors that had 2 modes, fast and slow. The fast mode resulted in changing the angle by 4.75 degrees every second. The slow mode was changing the angle by 2 degrees every second. Now, this was done back in the 1990, and this was cutting edge technology. And fast forward today, literally for $60, you can make this setup and better. You can have different rotation rates and set the motor to anything you want. But still, back then, this setup was something really special. So it's pretty impressive to see them doing it back then. So this guy used a 2% scale model of the F18 jet in the water channel. And he gives the dimensions of the model, but not the blockage ratio. So we come down here, we can see some dimensions here. So the blockage ratio is an important detail. It tells us how much this object is taking up the test sectional area. And from the dimensions given here, I estimate the blockage ratio of this object to be about 5%, which is definitely acceptable, but it's been a few weeks now where the papers we've looked at haven't given the blockage ratios, which is a really important detail. The blockage ratio can greatly affect the flow physics, and anything about 3% or greater requires corrections. And in my opinion and analysis, corrections don't actually give you the right results anyway, particularly if you're looking at the flow physics, because you are generally using empirical corrections for your object, which is not likely an average model. Your object is something different. So adding the blockage ratio is always good practice so the reader knows what we're looking at. Anyway, at around 5%, I estimate this to be okay, and the results are okay to go along with. So in figure 9, we see the jet mode with the injection ports highlighted just here. And there are a few ahead of the cockpit, and there is one at the start of each LEX, then a few scattered over the LEXs as they reach the wings. So that's pretty cool. We've got quite a few different regions to visualize the flow. So this model was pitched from 0 degrees to 50 degrees and from 50 degrees down to 0 degrees. So we see how pitching up and down affects the LEX aerodynamics and subsequent potential hysteresis. The yaw angle was varied from 0 degrees to 20 degrees, and the water velocity was set at 7.5 centimeters per second, which gave a Reynolds number of 5,500 based on the mean aerodynamic chord. So first, the researchers looked at the flow over the jet at static angles of attack. So in figures 15 and 16, we can see the flow viz, which we have to come down to the appendix. They have a lot of figures in here. And perfectly honest, they aren't great quality figures. We can see some things here, but in a lot of other figures, we can't see too much, but we'll go through them. Anyway, we'll see what we can see. So figures 15 and 16, we see the flow viz of this airfoil at different angles of attack. So 0 degrees angle of attack and 0 degree yaw, and 10 degree angle of attack and 0 degree yaw. So the pictures aren't that clear here, but I'll try to point out what is happening. So in the first picture, this is at 0 degree angle of attack. They pretty much have these leading edge vortices with, these leading edge extensions with the vortices traveling the entire span of the aircraft. You can see them coming over here, and then they hit this is actually upside down here. So the tail is down here, and this is the bottom of the aircraft. The vortices travel the entire length of the aircraft from the cockpit effectively, all the way down to the tail. So and they're very well behaved. And then when we go to 10 degrees, we still have them existing pretty much the entire way, and they are still quite well behaved. They do zigzag a little bit around, but they are still quite nice. So in figure 13, we see a diagram of the LEX Vortex flow physics. So let's go up to that there. So in this figure, we can see the flow physics of the leading edge extension and the vortices coming off there. And as we saw in podcast 163, the main vortex made by the LEXs induces a secondary vortex of opposite sign. So we have the main vortex here that rolls up around towards the fuselage. Then we have the secondary vortex down here. And this is very common actually when you have a vortex near the wall, especially if it's a large vortex. This large vortex induces flow near the wall and spins it up into another vortex. Now, this is pretty cool. So if that secondary vortex is strong enough, it will do the same thing and create another vortex of its own. So we have a tertiary vortex here, which we also do see. And this tertiary vortex, if strong enough, can do that again and create another vortex. Now, I guess this can actually go on until viscosity doesn't allow it to happen anymore. But the most I've ever seen, or at least the most I can remember seeing, is 4 vortices. So you have the main vortex, then you have 3 secondary vortices forming in succession. Here the researchers identified this main vortex from the LEX, then a secondary, and then a tertiary vortex. And I'm pretty sure there'll probably be other vortices as well, but the flow viz wasn't like that. The pictures weren't that great quality anyway, so I don't think you can really see too much once you can get down pretty close to the wall. Anyway, we can identify 3 here. And the way the main vortex is formed is that it sucks fluid from not only the suction side, but also from underneath the wing, from the pressure side, and that fluid rolls up into this main vortex. The other 2 vortices seem to be very isolated and really only exist between the wall and the main vortex, so they're pretty much cut off from the rest of the flow. So this main vortex also moves towards the fuselage. And now back to the static angle of attack. So in figures 17 and 20, so let's go down to the appendix again. Let's try to find these figures. As I mentioned, they have I think 115 figures in total, and we're looking for 117 and 20. From 17 and 20. Here we go. They show how the LEX vortices develop as angle of attack increases. However, the pictures aren't that great here, so I'll do my best to explain what is going on. We can see here at angle of attack 20 degrees, there is a little bit of a vortex forming, these black lines coming along here. Now, as the angle of attack increases, the LEX vortex breaks down farther and farther upstream. So for example, at 20 degrees, the vortex makes it all the way to the wing's trailing edge, and then it starts to burst. But at 48 degrees, so if we go down to 48 degrees, which is the next one, I think, we can't see too much, but the vortices don't even make it past the cockpit. So that's how much they just like the bursting occurs upstream. And that's not that surprising. I mean, this is very typical for LEXs and delta wings, so they operate in a very similar manner. And a delta wing is a wing plan form that is shaped like a triangle, the Greek letter delta, hence the name. And it also creates vortices that flow over the suction surface and suck the free stream air down to the plane. So this is for static angles of attack though. And we know that, okay, the airplane does sometimes fly at static like angles of attack. But what happens when you change the angle of attack dynamically? Because obviously to go to a different angle of attack, you need to change that, especially if you're in a dogfight or whatever. So pitching the plane up or down dramatically, the physics of the LEX vortices change. So for example, when you pitch the plane up from 0 degrees to 50 degrees, the vortices are tightened and smaller, which the author suggests means that the vortices are more stable. These vortices then burst at a higher angle of attack than if you were to pitch the plane down. So pitching the airplane down from 50 degrees to 0 degrees, while you cover the exact same angle of attack, the vortices behave differently. First of all, the vortices are larger, which the author suggests means that they are less stable. And the fact that they burst at lower angles of attack also agrees with that. So let's say you were to pitch the angle of attack from 0 degrees to 20 degrees. The vortex might start bursting at the wing trailing edge, whereas if you were to go from 50 degrees down to 20 degrees, the exact same 20 degrees, the vortex might start bursting behind the cockpit, so it's significantly further upstream. That's the hysteresis effect I was talking about. The same angle of attack, two different approaches to the angle of attack, and it changes how the vortex forms. And we know that the pitching up resulted in a tighter vortex and it was more stable. Now, when you do the exact same thing, so you pitch up or pitch down, but at a faster rate, you get the same general trends, but the vortices seem to burst earlier when the pitch rate is faster. So that means that regardless of whether you're pitching up or down, pitching at a faster rate means that the vortices burst much further upstream. So they're not as effective. So that's not as good. But while comparing these two dynamic movements show this, comparing the dynamic case to the static case show that the pitching up results in the vortices bursting farther downstream than if the plane is static. So still, dynamically moving the airplane is still better, generally speaking, if you're pitching up, than if it's static. On the other hand, if you're pitching down dynamically, that is actually worse than the static case. So the vortices will burst further upstream than the static case altogether. So if you were to rate these three different situations of pitching up dynamically, static, and pitching down dynamically, that's the order that you would rate them in terms of best to worst. So why would this be the case? Well, it seems that this flow physics requires some time to stabilize. When you're changing the pitch angle, you seem to have some effects of the previous angle of attack on the flow physics at the new angle of attack. When you go to the static condition, on the other hand, this is not the case because you pitch to a certain angle of attack and hold it there. Sure, during the initial pitching phase, you do get the dynamic effect, but once you hold it at the desired angle of attack, the flow stabilizes. And this is the major reason for hysteresis, as well as because of the history of the object's orientation can affect the object's aerodynamics, and that is literally hysteresis. So we can conclude from this section that the pitching angle of the airplane, when it's done dynamically, affects the LEXs vortices, and the faster you pitch it, at least in the range we looked at here, the farther upstream the vortices will burst. But dynamically pitching up results in the vortices traveling farther downstream before bursting compared to the static case, and dynamically pitching down has the opposite effect where the vortices burst further upstream, so that's not as good. Now, that is pitching dynamically. What about yawing dynamically? Yawing and pitching dynamically. So yawing refers to rotating the airplane left or right. And this is primarily done through the tail. However, in most planes and fighter jets in particular, there is some level of inertial coupling between the different control surfaces, which means that when you change the attitude of the airplane in one direction, that results in a change in the orthogonal direction as well. So for example, if you were to yaw the airplane, which means you turn it left or right, sometimes that is coupled with a roll as well. And in fact, it's often coupled with a roll, and sometimes even with a pitch. But yaw and roll are usually quite closely coupled, especially in modern fighter jets. But anyway, let's focus on the effects of yawing the plane on the vortices of the vortices flow physics. So they yawed the plane from 5 degrees to 20 degrees and at a bunch of angles of attack ranging from 0 degrees to 50 degrees. So can you imagine that? You're literally pitching up to 50 degrees, which is a really high pitch angle anyway, then yawing at 20 degrees, which is really high as well. The amount of G's on you would be insane. Now the authors say that in figure 41, we see the results when at an angle attack of 10 degrees and yaw angle of 5 degrees. So let's go down to that one there. I think it's page 80. Here we go. So I got it. It was page 80. Well, in this figure, I can't see too much. But anyway, this is a static condition. So the airplane was set there and the flow was allowed to stabilize before these photos were taken. I can see the vortices a little bit here on this figure here, but not too much. But anyway, the authors say that initially, the flow around a LEX starts off at two different segments. So we can see the upstream and downstream. So we see the flow, there are two segments in this picture. We can actually see them a little bit. The one on the underside of the LEX and then one on the top. And you can see that they don't actually join to begin with. Then the second one pops over the LEX and then joins the first one. And that motion there is when you had the flow over the LEX. That is when you effectively have the vortex forming. The two different streams wrap around each other and create that vortex. And that is how LEXs work and delta wings work as well. The flow comes from underneath over the sharp swept leading edge, and that creates the vortex. But anyway, here the authors say that the two segments mixing together leads to the vortex, which spirals along. But while this is the general flow physics, it does change depending on whether you're looking at the leeward LEX or the windward LEX. So the leeward LEX is the LEX that is being yawed away from the free stream flow, so this side here, and the windward LEX is the one being yawed into the free stream flow, so like you're sort of pushing that side into the free stream flow. So for the windward LEX, the flow physics is significantly simpler, with the vortex forming, bursting around the vertical tail. For the leeward LEX, the vortex seems to travel a little farther downstream before bursting, so this asymmetry between these two vortices of the windward and leeward LEXs forms. Increasing the angle of attack more at this yaw angle, so 5 degree yaw angle, and really the yaw angles considered, so 10 degrees and 20 degrees, the vortices produced become more symmetrical. So the higher angle attack you put it at, the less effect this yawing angle has on the vortices strength and how far they go downstream. I shouldn't say really strength because we don't know that for sure, but how far they propagate downstream, we do know for sure. However, as the yaw angle increases, this asymmetry does grow, and it takes a greater and greater angle of attack for that asymmetry to start to be balanced out. And so that is for the static conditions. We see that the yaw of the plane results in this asymmetry in the vortices produced off the LEXs in favor of the leeward side. And as angle of attack increases, this asymmetry reduces. But what happens when you dynamically yaw the plane? So the authors looked at the same pitching up and down at the same two rates of pitching up and down, but now at three different yaw angles, 5 degrees, 10 degrees, and 20 degrees. So interestingly, once the plane had reached about 10 degrees, while pitching up, the leeward LEX hasn't formed any vortex yet, regardless of the yaw angle. So the yaw angle seems to be suppressing the leeward vortex's formation during this dynamic pitching up to 10 degrees. But once the angle of attack increases, this vortex does finally form. Another important note is that the more extreme the yaw angle, the sooner the windward vortex bursts. It seems to follow the same trend as we saw with the no yaw, where as you increase angle of attack, the bursting point moves up and upstream towards the cockpit. Now, interestingly, as the leeward vortex forms, and it occurs at a high angle of attack, the leeward vortex seems to always burst farther downstream, regardless of the angle of attack you're at or the yaw angle. So the leeward vortex is generally a bit more stable than the windward vortex. So the trends we see here are pretty much consistent with what we saw in the dynamic pitching cases and the yawing cases, yawing static cases. It is literally just a combination of these two cases together. So it's kind of like a linear addition. Let's move on to the dynamic pitching down with the yaw angles. So the trends seem to stay the same, with the leeward vortex being a boss and staying intact farther downstream than that of the windward vortex, regardless of the yaw angle or pitch angle. It just is better. One final thing to note is that at some conditions, for example at the yaw angle of 10 degrees and an angle of attack of 11 degrees, while pitching up, one segment of the leeward flow jumped over the cockpit and went between the two vertical tails. That's pretty cool, and might explain why sometimes the liquid vortex didn't form, particularly while at long attack. So that also means that there's a significant change in the flow physics and forces. I mean, you now have a new stream of flow traveling around the tail. That is going to create some disturbances and cause the airplane to be harder to control. And that brings us to the end of this podcast, and there was a lot in it. So let's wrap up the findings we found. So for these LEXs, they create vortices. And when you are at a high angle attack, regardless of being dynamic or static, and even the yaw angle, the vortices will burst closer to the front of the plane as you pitch more nose up. Now, dynamically pitching the plane up means the vortices stay intact farther downstream, but dynamically pitching the planes down is worse because it makes them burst further upstream regardless of the angle of attack that you're at, really. It's always worse than pitching up. Now, yawing the plane results in the vortex from the side of the plane being yawed away from the free stream flow to remain intact farther downstream, that leeward side. But it also requires a higher angle of attack to form because at long attack, the second segment of flow required to form the vortex jumps over the canopy instead and flies away. So you can't get that vortex forming. And with that, we come to the end of this podcast. So if you like, make sure to like and click the subscribe button or the follow button, whichever platform you're on. And if you want to learn how to do open foam CFD, take a course in the link below. It takes you from being a complete beginner to being able to do DS simulations. And we also have other CFD courses as well as an instrument called the Atmosphere Hawk. So this instrument increases the accuracy of your experiments by 2 to 4%, and usually even more than that. And you can find out why in the link below. And I'll see you in the podcast. Peace out, amigos.